Okay, so in this video I want to talk about the Lagrange multipliers method of handling constraints. Okay, so Lagrange's method of so-called undetermined multipliers is commonly used for systems where there's more displacement degrees of freedom than there are independent degrees of freedom of motion. All right, so it's commonly used in rigid body dynamics, okay, but it can also be applied to static structural analysis where we have constraint equations that reduce our number of independent degrees of freedom. Okay, so the formulation for Lagrange multipliers, all right, is basically that we add unknowns into our system of equations. These are collected in a vector lambda of length equal to the number of constraints. All right, and it can be shown that these Lagrange multipliers, or these unknowns, lambda, correspond directly to basic forces within our system. And these basic forces are transmitted to the nodal equilibrium equations by the constraint matrix C sub f, which we know how to form. Okay, so these basically become additional forces, or excuse me, additional unknown forces in our system. So we add them into the left-hand side of our nodal equilibrium equations. Okay, this should be PF tilde, all right, kind of the total right-hand side vector, okay? All right, but these become unknowns. And then we can write this set of equations simultaneously with our constraint equations, which were something like this, all right, CF times UF equals R. Okay, so two sets of equations, we can write them simultaneously. All right, so the first set of equations is shown down here. All right, KFF times UF plus CF transpose times lambda equals PF tilde. And then this set of equations we write as CF times UF plus 0 times lambda, all right, equals R. Okay, so all of this stuff we know how to form. We know how to form this matrix. We can find KFF, we can find CF, and on the right hand side we can find PF tilde, or all the load effects, and then the right hand side vector for the constraint equations R. Okay, and then solve simultaneously for U sub f and lambda. All right, so we get the nodal displacements and the Lagrange multipliers from this one set of equations. Okay, so one of the advantages of the Lagrange multiplier method is it does not alter KFF like the transformation method and the penalty method do. Okay, so this is advantageous if you're looking at different load cases with different constraints. All right. Okay, however, this adds to the number of unknowns in our simultaneous equations. Okay, so the computational cost of solving equation 2 can become large, all right, if you have a lot of constraints. Okay, all right, but once we solve for those lambda values, which we'll show in another example, or in an example, all right, we need to use those to recover the reactions. Okay, and the way to do that is to map each Lagrange multiplier onto a basic force of the constrained elements. All right, so if we had an axially rigid element, then the associated Lagrange multiplier is a force that's applied to the element in order to maintain axial rigidity. Okay, and then if we had a flexurally rigid element, there's going to be two Lagrange multipliers. Let's call this lambda 1, lambda 2, lambda 3. Okay, these are forces that are going to be added to our element in order to impose UB2 and UB3 equals 0. Okay, and then of course for UB1 equals 0, the axially rigid case, this force lambda 1 is going to enforce the axial rigidity. Okay, so each Lagrange multiplier can be mapped to the axially rigid or flexurally rigid element that it represents. Okay, but basically when we get into force recovery, when we evaluate the element force deformation relationship, we have the basic deformations, basic stiffness, fixed in basic forces due to member loads. We're going to have some additional basic forces due to Lagrange multipliers. Okay, so we just need to be sure to add those in when we're doing force recovery. Okay, but at the high level, solving equation 2 is straightforward after we've assembled all of these objects. Okay, and again, this should be PF tilde. All right, but we just create a large left-hand side matrix, call it KFF lam, that's just partitioned off based on the number of unconstrained degrees of freedom and the number of constraint equations. Okay, so we initialize this matrix to be all zeros, okay, and then we write into the upper left block from row 0 to NFDOF and column 0 to NFDOF, we write in the KFF we assemble for the unconstrained structure, and then in rows 0 to NFDOF, and then rows NFDOF to NFDOF plus the number of constraints, or excuse me, columns NFDOF to the to NFDOF plus number of constraints. We write in CF transpose, which is over here, and then in the lower left block, okay, the lower rows and then the columns 1 through NFDOF, we write in CF, and then everything was initialized to 0, so we get that. Okay. Likewise, we can just concatenate our nodal load vector PF and R together. Okay, to form PF lam, and then we can just solve this matrix, that vector, against each other to get our vector of nodal displacements and Lagrange multipliers, and then pull out the nodal displacements from the first NFDOF entries, and then pull out the Lagrange multipliers from the trailing entries. Okay, then we can recover our basic element forces, okay, as we'll show in an example. All right, but I just wanted to give a brief overview of how these equations are formed and solved at the structural level. Okay, thank you.